In the last video for section 3.1, we showed that congruence mod 2 was an equivalence relation. And really, if you look at our proof, we didn't really need the 2 that much, that we could generalize this to say that congruence mod m is always an equivalence relation. So some other ways of phrasing what we've seen so far. So x is congruent to y mod m when x is equal to some constant k times m plus y for some integer. So x is congruent to the remainder in the division of x by m. So x and y are congruent if and only if x and y have the same remainder when divided by m. This is going to help us out in the examples on page 3. So if we have an equivalence relation, then we can talk about equivalence classes, just like we did in 2.2. When we're working with congruence mod m, we call these equivalence classes congruence classes. And this is the notation that we use for them. So z with a little m to show what our mod is that we're working with. So any two congruence classes, just like with equivalence classes, are either equal or disjoint. They'll be equal to one another if and only if x is congruent to y mod m. So if r is the remainder, the congruence class of x will always be congruent to the congruence class of the remainder when we're working in z mod m. So we'll always have m distinct congruence classes and z sub m. So let's look at this with an actual number. So the distinct congruence classes in Z3. So we're going to be looking at 0, 1, and 2. So as it said there, from 0 to m minus 1. So things that would be in the congruence class of 0 mod 3. So these are things that have the same remainder as 0 when divided by 3. So 0 will always be in its own congruence class. It's that reflexive idea. So we know we'll have 0, but 3 divided by 3 has a remainder of 0. 6 divided by 3 has a remainder of 0, 9, and so on. And also in the negatives, so negative 3, negative 6, negative 9, and so on. So this is an infinite congruence class, but it's all the numbers that are congruent to 0. So all the things that have the same remainder, a remainder of 0 modulo 3. So 1 is in its own congruence class. So we're looking for other things that have a remainder of 1 when divided by 3. So 4 divided by 3 leaves a remainder of 1. 7 divided by 3 leaves a remainder of 1, since 2 times 3 plus 1 is 7, and so on in the positive direction. So now going the other direction, thinking about this, negative 2 will be congruent to 1. So negative 2 divided by 3 will be 0 times negative 2. We'll have negative 5, and so on this direction as well. So you can see that essentially we're counting by 3's here. Last with 2, so 5 has a remainder of 2, 8 has a remainder of 2, and so on. Going back the other direction, negative 1 has a remainder of 2 when divided by 3. Negative 4 has a remainder of 2 when divided by 3, and so on in that direction. So think back to what we did on the very first page when we were working with those negative numbers and writing out our division algorithm, that we have to be careful as we're working with those to make sure that our remainder always ends up as a positive number. So this is the idea of a congruence class, in this case mod 3. You can almost think of it, a lot of times I think about, so we've got 0, and then 1, and then 2, and then when we get to 3, we're back to 0, and 4, and 5, and then 6, and 7, and 8. We just keep going around. So we have 0, 1, 2, and then at 3, we're back to being congruent to 0, and 4, and 5. At 6, we're back to being congruent to 0, and 7, and 8, and so on. And if you went the opposite direction, so from 0, going back the opposite direction at 2, we'd have negative 1, here we'd have negative 2, and negative 3, here we'd have negative 4, and negative 5, and negative 6, and so on from there. So you can start to kind of build your congruence classes by thinking through this pattern that we're working with. So if it was Z4, instead, do 0, 1, 2, and 3, and then work your way around. So this will be 4, and 5, and 6, and 7. And then 8 will be in the congruent class of 0, and 9, and 10, and 11. And just like that, you start to build your congruence classes just by thinking through this little diagram. So if you're more of a visual person, that might help to kind of think through what's happening. So we can define addition and multiplication with our congruence classes in modulo M. So when you add two congruence classes together, we'll add those numbers inside, and also with multiplication. So look at how we want to write our answers though. We'll write them as a congruence class, and we want R to be between 0 and M, where M is the mod that we're working with. So in this case, the congruence class of 9 plus the congruence class of 11. So we add 9 and 11 together, and we get 20, but we can't stop here because this is not something, we want something between 0 and 14 if we're working in Z15, so modulo 15. So we're thinking about the remainder. When you take 20 and divide by 15, that remainder is 5, so this is congruent to 5. And so we give our answer between 0 and 14. Same idea here, 12 and 25, we get 37. So what I think about 37 divided by 7. I know 37 is 5 times 7 plus 2, so a remainder of 2. So this is congruent to 2 when we're working modulo 7. So now multiplication, same thing. 9 times 3 is 27. So I think about the remainder when 27 gets divided by 4. That remainder is 3. 8 times 11 in Z5. We can go ahead and just multiply these. If it gets kind of a large number, another option is to rewrite, for example, you could rewrite 11 in Z5 first. So we could think of this, another way of working with this, 11 is also equal to, so 11 divided by 5 leaves a remainder of 1. We could have done that with the 8 as well. That 8 divided by 5 leaves a remainder of 3. So we could simplify first and then do our multiplication. We end up with 3. If you did just the 8 and the 11, you get 88. 88, if we divide by 5, also ends up with a remainder of 3. So you could simplify first and then multiply, or you can multiply and then simplify. It works out the same either way. For ones with exponents, the simplifying first idea helps us a lot. So 11 to the 8th power is a big number, and then it's going to be a little more work to simplify. So instead of just starting in with 11 to the 8th, let's simplify that 11. So as we saw in the example before when we're working mod 5, 11 is congruent to 1 mod 5. Well, now we have 1 to the 8th power. We can bring that 8 inside our congruence class. So 1 to the 8th is just 1. And so rather than having to figure out 11 to the 8th power, which is going to be a large number and a lot of simplifying to do, use this idea of congruence to simplify first, and then it makes it easier to simplify our answers from there. You'll see a lot of examples of these in the core problems, so a lot of opportunity to practice this skill.